Hello, and today we're going to talk about steady state approximation. So steady state approximation is really just what we call it when we're doing rate laws based off of reaction mechanisms, where the first step is not the slow step. The slow step could be the second or third or fourth or whatever. And now for this first step, it says equilibrium fast. We're going to do a whole unit on equilibrium later on, actually. Really, once we get to Unit 7, everything has to do with equilibrium. So we'll get to that. But right now, what you need to know is that if you have an equilibrium reaction, it's going to be a reversible reaction, which is why you have a double arrow. And this one kind of looks weird. Usually we write it like two arrows going back and forth. It's a reversible reaction. And that typically is not going to be your rate determining step because it's reversible. So whatever the other reaction is your slow step, or if there's multiple, that will tell you which one's the slow step. Now, when you're doing this, you still want to write out the rate law. You still want to write out the overall reaction by adding up the reactions like that. We've got 2A plus B on all of the reactants plus C. And then we have B plus D, and B cancels out. B is an intermediate. So my overall reaction is 2A plus C yields D. Now, because the slow step is the last step, this rate law is based off of the slow step plus anything before it, which we just did. We added up the slow step and the previous step. So that means I can write my rate law based off of that slow step and the fast step added together. So the K is the A squared, and then C. Because there's 2A, the 2 becomes an exponent, and the C, there's just one of those. So again, it's just the slow step plus everything before the slow step. So here's another example. They give us the overall reaction. And then they have, this is a 3-step reaction. The first step is a fast equilibrium reaction. It's just the double arrow, okay? And they're showing us that there's 2 rate constants here. There's a rate constant for the forward reaction and a rate constant for the reverse reaction. You don't need to worry about that because it's our fast step. It does not determine the rate. The slow step is the second step, and then the fast step is the third step. You can still add all 3 together to add up to the overall, but we don't really need to do that since they gave us the overall. What we do need to do is add up the slow step plus anything before it. So just these 2 steps. So we've got the B will cancel, it's an intermediate, and the D will cancel, it's an intermediate. So I'm left with 2A yields E plus C. And so my rate law is based off of that. It's Ka squared. Now again, that's the slow step plus anything before the slow step. Alright, here's one more example. Reaction is supposed to take place in the following 3 steps. If the rate law was found experimentally to be rate equals K AB squared times C squared, which step must be the slow step? Now for this, it's really easy to just check. Let's check to see if the first step is slow. If the first step is slow, it's based only off of that first step. Rate equals K AB times C, just the reactants. That does not match the given rate law, so 1 cannot be the slow step. 1 must be a fast step. So if I check to see if step 2 is the fast step, I need to add up the first 2. To see if step 2 is the slow step, I need to add up the first 2 steps. D is an intermediate, and you wind up with AB plus 2C yields E, and the rate law would be K AB times C squared, which still does not match. So step 2 cannot be the slow step, that also must be fast. Now by process of elimination, 3 must be the slow step, but let's go ahead and take a look at it. We want to write all 3 of those steps added together. Slow step plus anything before it. D is an intermediate, E is an intermediate. We're left with 2AB plus 2C yields F, and so our rate law is K AB squared times C squared. And that one checks So step 3 is the slow step.